reactions of haloalkanes with metals and some reactions of haloarenes. What are the metals which can react with haloalkanes? The metals are reactive metals. What are those reactive metals? Reactive metals are sodium, zinc, lithium and magnesium. Sodium Na, zinc Zn, lithium Li, magnesium Mg, the symbols. What is the reason for reaction of haloalkanes with these metals? These metals are very reactive. They are electron donors, electron giver, easily lose electrons. Sodium can lose electron 1, zinc 2 electrons, magnesium 2 electrons, lithium 1 electron. That electron donor or electron donation, this electron can be taken by the molecule like this. Rx is haloalkane by this part of the molecule, halogen part. Since it is electron negative, electron acceptor, X is electron acceptor, it can take this electron and breaks away as X minus. Here X stands for halogen atom. Maybe chlorine, bromine, iodine, like this. After that, the chemical bond follows the reaction is supposed to follow. That is the reason for the reaction of haloalkanes with these metals. Let us see what type of reactions we can see with these metals. With sodium metal, the molecules of haloalkanes, I am taking this depicting the chemical reaction Rx, there are 2 molecules involved in this step of reaction, 2 Na, 2 sodium metals atom, 2 atoms of sodium, reaction like this. The chemical bond between the carbon and X, carbon of this R group and the carbon of the R group X breaks. This portion is completely breaks away, combined with sodium forming NaX, sodium alloy. If this is chlorine, it becomes sodium chloride. If this is Br, it becomes sodium bromide, like that. And remaining fractions, these two combine are chemical bond between the carbon of this and carbon of this. New chemical bond, the carbon is forming and resulting this molecule. This will result increase in the chain of reaction. It is also called ascent of chain, hydrocarbon. This reaction takes place in dry ether. So, dry ether medium in which the reactions of haloalkanes with the metals, all of the metals take place in this solvent medium or liquid medium. This is organic liquid medium, dry ether. Why it is dry? Moisture should not be there, or water molecule should not be there in the reacting system. The reason, these metals are highly reactive with water, sodium, zinc, lithium and magnesium, forming corresponding hydroxides. Before the reaction being happened, the metal react with sodium, that is metal react with water. Just to avoid that, always use a dry medium. Use a dry medium or a dry organic solvent medium, dry ether, completely dry ether, in which the reaction is possible like this. Let us see the examples of this reaction. Now write what is R. If the R is ethyl, that is C2H5, CS3CS2, CS3CS2, same reaction like this. This is removed as this, resulting in the formula CH2 CH3. There is combination. There is CH3 CH2 ethyl. New chemical bond between this carbon and this carbon forming this. That is butane, of course. Is alkane. The chain is elongated. The chain is increased. That is alkane formation with increase of chain. That is the characteristics of the reaction. And this is the sodium. What is that? Alkyl group or alkane derivatives. Same reaction. If one is alkane, other is aromatic. If one is alkane group, other is aromatic group. The same reaction takes place. Of course, is ClCl, the chloro derivative of benzene. Carbon here. There are 6 carbon atoms, benzene, carbon with this Cl, eliminated as NaCl, and chemical bond with the carbon of this and carbon of this benzene forming this chemical bond. This is the aliphatic group, aromatic group. That is, carbon chain is increased. It is also called substitution of alkyl group into the benzene. This reaction is called as Wurtz-Spitting reaction. This reaction is called as Wurtz reaction. If both are alkane, that is alkyl group, it is Wurtz reaction. If one is alkyl, other is benzene, it is called Wurtz-Spitting reaction. Aliphatic, aromatic. Here aliphatic. Here aliphatic, aromatic, Wurtz-Spitting reaction. If both R group are aromatic, benzene, bromobenzene, benzene, bromobenzene. Aromatic, similar reaction, NABR formation, resulting in a new chemical bond between the carbon of this, forming a chemical bond. It is called as diphenyl. Two benzene are connected by chemical bond, sigma bond between this carbon. Diphenyl or biphenyl. Dry ether is the medium. This reaction is called as Spitting reaction. Difference: Wurtz reaction, Wurtz-Spitting reaction, Spitting reaction. Difference is both are alkanes. Here one is alkane, other is aromatic. Both are aromatic. That is, this is the one using for preparation of what is called higher hydrocarbons, like this. In the other case, zinc is a bivalent. It is the one we can donate 2 electrons. Similar reaction, the same chemical reaction. Zn plus X, Znx2. This gives same higher alkane, RR. Same type of reaction. This reaction is known as Falcon reaction. Falcon reaction. With other metal, lithium, and that is alkyl halide, haloalkane. Lithium is what is that? Electron donor. It donates 1 electron. 1 electron forming what is that? Lithium oxide, lithium halide. And one more lithium atom combines with this alkyl group, alkyl lithium formation. That is the chemical bond between the carbon of this and the metal lithium. Carbon metal bond. This combination, this compound. And this compound itself has no significance. These are higher alkanes, synthesis of higher alkanes. But this can react with a compound like this, that is cuprous iodide. 2 molecules of this combine to give a compound like this. Dialkyl lithium cuprate. It is a chemical bond. These two form chemical bond, new chemical bond with this, and this forms a chemical bond with this, a lithium and one lithium iodide. This compound is important. It is Gilman's reagent. This compound can react with any, that is haloalkane or alkyl halide. That is, let's with R dash, may be same or different. this compound or reagent is important reagent in organic chemistry. This reagent can react with haloalkane like this, forming higher alkanes R dash, and it is alkyl cuprate and lithium halide formation. So this reaction is very important. This is also preparation of higher alkanes. This synthesis is called as core house synthesis of higher alkanes. Just compare this higher alkane formation, higher alkane formation, higher alkane formation. Among these, this assumes greater significance because this reaction used in the synthesis of what is that higher alkanes of linear as well as side chain or branches, that is all types of higher alkanes, different types of higher alkanes we can make, that is branches of hydrocarbons, side chains or linear chains. But using this reaction we can use simple or asymmetric reaction like this. A simple alkane, that is higher alkanes we make. That is the difference. So this finds a greater application than this. So all these reactions with metal found to make what is that? The alkanes from lower alkanes to higher alkanes, the bigger alkane molecules, preparations, they are useful over here. Next, a reaction with magnesium. Magnesium also react with metal. It contains 2 electrons in the valence shell, electron donor, 2 electrons can donate. So this electron can donate, no, magnesium can donate one of the electron. This is haloalkane, chemical bond. When the chemical bond breaks symmetrically, taking back the electron, addition of this electron give electron to become what is that? X minus, negative charge, that is chloride or bromide like that, halide. This forms a free radical. And after electron is donated, Mg becomes this one electron left with and becomes positive charge after losing electron. This electron with this electron, this behave like a free radicals. These free radicals combine, these 2 electrons join to form a chemical bond like this shape. Bond between the carbon and metal. This and this again result what is that? Bond between the magnesium and this. Magnesium and halide, this is ionic, 100% ionic. This is not fully ionic, covalent as well as ionic, 50% each. That is a type of chemical compound formation. This chemical compound is called as Grignard reagent. Grignard reagent, this is a mechanism for this formation of this. And after the Grignard reagent formation, it is stabilized by the solvation of the ether. Again, this reaction is taking place in the dry ether medium. After the product formation, it is getting stabilized by the solvate. It is solvated by the molecules of ether. This is stabilized. Just what is that? Prevent the back reaction. That solvation will prevent the back reaction. It remains stable over here. This compound finds a lot of application. This is a very important reagent in organic chemistry. Using this reagent, we can synthesize different organic compounds. You know, organic compounds, different types of alcohols is one type of organic compounds, and different types of aldehydes, one more type of organic compounds, and different types of ketones, different types of amines. So variety of hydrocarbons, organic compounds we can synthesize using what is our Grignard reagent by taking different group of R group. That is the application of Grignard reagent. This is a reaction by which we make Grignard reagent. And in this, what is that? This is a halide group. That is a carbon. That is like this, halide like this. Just like the same example. Here carbon here. Here is Br. The entire thing is R. You can just mention. This is carbon here. Carbon is not mentioned. Bonded to bromine, bonded to CH3 group, C2H5H. Different groups. Then this carbon is called as asymmetric carbon. Asymmetric carbon, and 4 chemical bonds written like this, but in tetrahedral fashion. Tetrahedral fashion. So with the different groups are there, after the MgX is substituted, what type of molecule geometry we get? We get what is that? That is geometry, same side Br. We get the geometry like that, Ba, Mgr on the same side. Same geometry. That is, geometry means stereogeometry. Stereo, that is different orientations, same side. Geometry is retained. But in some molecules, this is MgBr is on the reverse in the opposite direction, H this side. In the opposite, it is inversion. This geometry, stereogeometry is inverted. That is exactly mirror image of these two, inverted inversion. Why this is the case? As I already told you, discussed earlier. Here the carbon in tetrahedral fashion, after this chemical bond breaks away, forming this radical, that is free radical. Free radical with after the chemical bond disappear, only 3 chemical bonds remain. 4 chemical bonds always tetrahedral fashion. 3 chemical bonds, that means the planar. That becomes, that is carbon with the planar 3 chemical bonds. Now this carbon is deficient of what is one bond, so that bond can attack by this, forming MgX, either from above the plane or below the plane. Both are possible. So if it attack from above the plane, we get this. If this attack from the below the plane, we get this. That is why both are possible. You get different, there is an intermediate formation. So with this formation, then this formation, therefore both isomers are possible. Retention and inversion, 50-50%. 50% of this, 50% of this. So that is the geometry of this. What is that? If the carbon is what is that? Asymmetric carbon. Is another example. Here R may be aliphatic or a mixture of aliphatic or aromatic. That is aliphatic group. CH2 is aliphatic. Is benzene as a substituent? Br. This Br is changed into MgBr. That is an example of Reynolds reagent. That is, this is called as benzyl group. Benzyl bromide. It becomes benzyl magnesium bromide. Benzene with CH2 is called as benzyl. That is an example of Reynolds reagent. So this is a preparation of that is Reynolds. What is Reynolds reagent? How it is prepared, and what are the possibilities of geometry if carbon is asymmetric, and their applications discussed. This is about the reactions of haloalkanes with metals. Now let us move on to some reactions of haloarenes. Look at this Rx. If R is alkyl, aliphatic, this chemical bond is reactive. This chemical bond is reactive. If R is aromatic like this, benzene with this X, this chemical bond is less reactive. Difference between the chemical bond between the halogen and the carbon of aliphatic and the carbon of benzene. The difference is, that is the case, is less reactive. That is aliphatic, it is more reactive. And we see that seen so many reactions we have is that undergo these molecules undergo so many nucleophilic substitution. That is, replace this by this X is removed as X minus and added as other minus nucleophilic negative charge particle like this. That is called nucleophilic substitution. Since the bond is less reactive, usually this will not take part in chemical reaction. This will not undergo any kind of, that is usually rarely undergo nucleophilic substitution. If there is a nucleophilic substitution, it is only under drastic conditions. That is stressful condition, forcible condition. We set the chemical bonds to break forcibly under stress, then the reaction is possible. Stressful, that is why one such reaction is that, what is that? Preparation of what is that? That is phenol from chlorobenzene. That is Chloro-derivative of benzene, haloarene. So here Cl is replaced by OH minus. It becomes phenol. This is called as phenol. This reaction is taking place, that is with sodium hydroxide. Hydroxyl ion is here, but requires very drastic condition, that is high temperature, high pressure. So with this, what is that? These are byproducts eliminated. NaCl is a byproduct, HO is byproduct, and NaO attack. First, it is Cl is replaced by ONA. This is called as sodium phenoxide. This is called as phenoxide formation. Then it is acidified to remove Na and replace H plus. That is phenol formation. We get NaCl and phenol formation. Overall, Cl minus replaced by OH minus nucleophile. This is under very stressful condition, drastic condition. It is possible. So because this chemical bond is less reactive, very rare reactions like this. So this is the one what is usually used, this reaction used in the industrial production of phenol, because phenol you are finding very important compound is a disinfectant, antibacterial, antiviral, that is external the washing in bathrooms or the cleaning of what is that the area where it is highly infected with bacteria like this, phenol. So in the large scale, we make this phenol by industrial production using this reaction. This reaction is called as DOS process. This is one reaction. And the remaining reactions are a reaction with benzene. It is the presence of double bond, pi bond. These pi bonds can react. So this pi bond reaction is only by electrophilic substitution, not by nucleophilic substitution. What is electrophilic substitution? Here chlorobenzene is here. With this, what is that? Carbon with chlorobenzene, only one carbon. This carbon with hydrogen. Carbon with CH is there. Here 5 hydrogen atoms. Then only one of the hydrogen atom we replace. That is H is removed as H plus. A plus. The plus are radical. Positive ion is substituted. That is called electrophile. Carrying positive charge is called electrophile. So if H is replaced by this, it becomes this. H is replaced by H is here. It is called electrophilic substitution. Electrophilic substitution. Removal of one hydrogen like this from this. So these reactions are common. Electrophilic substitution reactions are common. Different electrophiles you can generate using different reagents. And before going to talk about the electrophilic substitution, the products obtained, let me talk about the presence of chlorine plays an important role. It is chlorobenzene. This chlorine is a dual character. One is minus I effect plus M effect. Minus means inductive effect, negative inductive effect. Wherever the chlorine is bonded to carbon, these bonding electrons are pulling towards it. That is called electron withdrawing group. The halogen atoms are electron negative atoms. They withdraw electrons. They pull the electrons. What electrons? The sigma bond electrons towards it. Electron pull or electron withdrawing group. This effect we will see all over this electron density. Here this pi bond or electron causing electron density in the benzene will reduce electron density. The electrophilic substitution mainly depends on electron density. Any reduce in the electron density will what is that? Will difficult to find electrophilic substitution like this. Minus negative effect, that is inductive effect, negative inductive effect. And this chlorine not only has negative inductive effect, there also another effect is there. It is mesomeric effect, positive mesomeric effect. The reason all the halogen atoms contains 3 lone pair of electrons in the valence shell. That is bond pair of electrons forming chemical bond. Among these 3 pairs, one pair will take part in delocalization of electrons, because these electrons are delocalizing and giving these electrons into benzene, that is positive mesomeric effect. These lone pair of electrons also involved in delocalization with pi bonds. It is called positive mesomeric effect, giving into positive. If the electrons are taking back these other groups present, what is the electron withdrawing group, then withdraw electron, positive electron is pair of electrons towards this. It is called minus effect, but here plus M effect. Because of this plus effect, that is, it will activate the benzene. This will activate the benzene, this will deactivate the benzene. But among this effect, when you see that this effect is more than this effect, therefore slightly less reactive. Benzene, that is chlorobenzene, is actually less reactive than benzene because of this property. This will what is that? Will make activate. This will activate the benzene. This will deactivate the benzene for electrophilic substitution. But overall, this effect now will reduce or deactivate the benzene to little extent, is less reactive than benzene. That is why, so even then, this chlorobenzene undergo electrophilic substitution forcibly. And what kind of electrophilic substitution? This presence of chlorine, that is plus M effect, is what is that? Ortho and para director. That is, chlorobenzene has a position is there. This point is called as ortho. Both are same. First, second point. This carbon and this carbon. This point is called as ortho. Both are same. This point is called as meta. This both are same. But this point is called as para. Either this or this. So this is para and ortho director. The presence of chlorine will allow electrophilic substitution either at ortho and para. Both use. Ortho substitution and para, but will not what is that, will deactivate. This plus MA will deactivate the substitution at this meta position. That is why only two kinds of derivatives you find. The reason for this, it is this following resonance. The resonance is there when these electrons are shared into the benzene ring. These pair of electrons form a chemical bond, pi bond, positive, and this chemical bond breaks. This electron pair move on to this carbon, positive, negative charge. This is one resonance form, this another resonance form. Same molecular structure, only electronic structure changes with electron, what is our electron movement. Pair of electrons are moving in the ring. Now this pair of electrons form a chemical bond with this, like this, this carbon. Then this chemical bond naturally breaks, and here electrons are concentrating here as negative charge there. The next instant, these chemical bonds form a chemical bond between these two, and this chemical bond breaks and becomes a negative charge. That is, two electrons on this carbon making negative charge. And next is that these electrons make a chemical bond and breaking back into this, forming again the chemical. That is, same compound is formed, same structure is forming. That is, resonance keep changing. This resonance structure stabilizes, and therefore you see that this position, this are same. This position and this position, ortho position and para positions are what is that? Negative charges. Easy, that is, negative charges is creating a slightly negative charge at this carbon and this carbon, ortho and para. This will favor the attack of positive charge because negative positive. So replace this hydrogen easily. Both are possible. Therefore, this chlorine is a ortho director, para director. So both are possible. So electrophilic substitution in some molecules Here substitution taking place at this, remove the hydrogen as H plus. In some other molecules, the substitution taking place at this, remove this hydrogen as H plus and this is substituted. Both are possible. So this is also possible. This isomers electrophilic substitution. So this electrophile is substituted. That is, this kind of reactions are common in what is that? Haloarenes. What are these examples of electrophilic substitutions? These are the electrophiles generated. Different types of electrophiles. It is called as chlorination. Benzene is further chlorinated. Chlorination using the reagent, this reagent, chlorine plus anhydrous aluminum chloride. The action of this reagent on the chlorobenzene and this combined with this, there is substitution here. It becomes dichlorobenzene. It is ortho-dichlorobenzene, para-dichlorobenzene. With this reagent, it is chlorination. Already chlorinated, further chlorinated, comes disubstituted. Two types of isomers you get, because this chlorine is a ortho-director and para-director. Next electrophilic substitution is electrophile is nitrate. That is, nitration is electrophilic substitution. The reagent for the generation of nitro group, that is plus group, is concentrated HNO3 and concentrated H2SO4. Mixture of this, warming this generates the positive charge, negative charge, positive charge, negative charge. The positive charge can attack this, forming two compounds. Here, with this reagent, nitration mixture, chlorobenzene with nitration produces nitro derivative ortho, a nitro derivative para, mixture of this. This is common, this only different electrophile. Another electrophilic substitution, it is sulfonation. HSO3 plus. It is generated by strong, very strong sulfuric acid. This strong sulfuric acid is OH minus and this. Distill substitute here. HCO3 sulfonation. So sulfonation derivative of chlorine, ortho and para, like this, mixture of this. Then H plus and OH minus combine H2O like this. This will combine with this H plus, this minus. And next is, if this chlorobenzene is treated with this mixture, what is that reagent, that is methyl chloride, that is also called Friedel-Crafts reaction, anhydrous aluminum chloride, and there is alkyl halide, aliphatic halide. It gives chemical bond breaks, resulting in what is the CH3, that is electrophile, that is alkyl electrophile is generated, and this electrophile can attack some molecules here, some molecules there, mixture of, that is ortho and para. This CH3 is called as toluene. It is called chlorotoluene, ortho-chlorotoluene, para-chlorotoluene. If CH3 is here. Next, last one, it is a generation of acyl, what is that? Acyl electrophile, CH3CO plus. By this reaction mixture, again, anhydrous aluminum chloride, CH3COCl, acid chloride. This will take this as Cl minus and plus generated, C plus. This is acyl group. If this acyl group produces C, it becomes what is that? COCH3 becomes the ortho derivative. Here COCH3 para derivative. That COCH3 is called acetophenol. Benzene, that is COCH3 acetone, that is ketone. Acetophenol, chloroacetophenol, here chloroacetophenol, ortho-chloroacetophenol, para-chloroacetophenol, mixture of isomers. Likewise, so this is the same reaction, mechanism reaction same, but different electrophiles. If you use different reagents, generate different electrophiles, you get different types of products. You get electrophilic substitution. So with this chlorination, we get this. With nitration, we get nitro derivative. With sulfonation, we get sulfo derivation. With Friedel-Crafts reaction, we get following the alkane derivatives. With acyl derivative, get acylation mixture. So with this, we have completed the chapter haloalkanes and haloarenes.